Good. So we're going to, it's been a while since we've done related rates, right? We spent some time Friday starting related rates, but this week was mainly getting ready for our Chapter 2 test. So it's been a while since we've seen this. But what I want to do is I want to, we did the first page, right? So I want to recap. I want to spend time going over these problems again, just highlighting the steps, since it's almost been a week since we've seen this. And then we're going to spend today just going over 3 and 5. It's going to probably take the whole period just to go over these two problems. Okay. We talked about how related rates is similar to implicit differentiation because we have these d over d. Remember, with implicit, we have dy over dx. But we only did it for the y's, right? We didn't do it for the x's because x was already the independent variable. So everything was already with respect to x, so we don't have to do anything additional with x's. But now the difference is with related rates, our independent variable is now time. So every variable is going to be impacted by time. So if it's x, it'll be dx dt. If it's y, it'll be dy dt. If it's r, it'll be dr dt. So as soon as we find any variable's derivative, we need to attach a d over dt for that variable. Right. So it's going to look messier because every variable is going to have its own d over dt, and we're going to see d over dt all over the place. But at least the derivative is relatively easy. Well, at least it should be. It should just be power rule for most of it. There's one exception where you're going to see product rule, and that is with area. But most everything else, we shouldn't have to do anything more than power rule. Okay. The challenging part is figuring out where the pieces fit, what values to assign the variables, and how to set it up. But the calculus should feel easier than what we've seen from before. So let's look at example 1 here. Example 1, it says we talked about we're dealing with area of a square. So we knew that area of a square is just length times length. I used x as my variable, so I say a equals x squared. Okay. And then after we have a equals x squared, we always find the derivative with respect to time. So a becomes 1 dA dt. And then x squared becomes 2x dx dt. Right? We're just finding each of these derivatives, but then we're inserting the appropriate d over dt for that variable. So for a is dA dt, for x is dx dt. Now, each of these variables represents something for our problem. X represented the length of the side. Dx dt represented the rate of change of the length of the side. So basically, this tells us how fast the side length of our square is changing. dA dt tells us how fast the area of the square is changing with respect to time. So we know we have 3 variables, and we want to read the problem to see what information we have and what information we're looking for. So if we look at the problem here, it says the sides of a square are increasing at a rate of 5 centimeters per minute. We see 5 describing the side length, but it's not just side length, right? We see some variation to this. We see these words like increasing. We see these words like centimeters per minute. So that indicates to you there's something more than just x, right? This is the rate of change of x. So we say dx dt is 5. The next decision we had to make was what to do about the sign. Do we keep this rate as a positive or a negative rate? And for this problem, we see the sides of the square is increasing. So because the side is getting larger over time, we want that rate to be positive. So we're always going to have to manually adjust that sign based off of this, the description in the problem. If the problem said the size of the square is decreasing, then we have to make that a negative. Okay. How fast is the area increasing? So we're looking for dA dt, that's the unknown, when the sign measures 15 centimeters in length. So we know that 15 is a static value. Notice that it just says centimeters, right? There's no time involved. So 15 is just that x. And once you have these two variables figured out and you know you're looking for dA dt, we can now plug into our equation and then solve for dA dt. Our units of measure, area has its own unit, time has its own unit. So area is a two-dimensional unit, so square centimeters or centimeters squared. Time is minutes, so we just put them over each other, centimeters squared per minute. Okay. Make sure you're not saying centimeters per minute squared, right? That's something else. That's acceleration, right? All right, any questions with number one that we went through last week? Okay. Number two was the Pythagorean theorem problem. We had the picture of a ladder sliding down the wall, but it's also getting dragged towards or away from the wall. And we see that the shape that's created by the ladder, the floor, and the wall is a right triangle. So with a right triangle, we know that we're dealing with Pythagorean, or we use Pythagorean theorem so that we can connect those three pieces of information together. So once we built our equation using Pythagorean theorem, a squared plus b squared equals c squared, but in this case I used x, y, and z. We found the derivative, right? So we found all these derivatives, but then we attached a d over dt for each of those variables. We read the problem and we gathered information. We found some missing piece using Pythagorean theorem. We realized that the ladder is not changing over time, so we made that a 0. We know that the base is being dragged away from the wall. So even though it's moving left, we don't care about the direction. We want to know what's happening to that length. This length is getting longer over time, so we want that rate to be positive. So that's why it's positive 3 feet. Now, if the ladder was being pushed towards the wall, then we expect that length to be decreasing, and then we will make that negative. So you always want to visualize what's happening to your values, and then make your decision for your signs. The ladder is also dropping down, so we expect this value to be decreasing, this length to be decreasing. So that's why we make dy, or it ended up where when we plugged everything in, our dy dt ended up being negative, and that's consistent with what we know. The negative has nothing to do with it going down, it's because that value is getting smaller. The second part that we dealt with was finding the rate of change of the area of this triangle. So we know that area of a triangle is 1/2 base times height. If you, we know that we have two variables sitting next to each other. If we want to find the derivative, we got to use product rule. So then we did f prime g plus f g prime. A lot of variables show up, but we have enough information from part A to plug in and find that missing value. dA dt is the rate of change of area with respect to time. And so area is square feet, time is seconds, so square feet per second. Okay, let's go to the back page. And let's look at number 3. So the problem reads, a spherical balloon is being inflated at a rate of 10 cubic centimeters per second. Find the rate of change of the surface area of the balloon at the moment when the surface area is 64 pi. So we have a balloon, you see cubic centimeters, you see surface area, so we need 2 equations that we need to use. And those are volume and surface area of a sphere. So let's write those down. So volume formula is 4/3 pi r cubed. That's volume for a sphere. We also have surface area of a sphere, which is S is equal to 4 pi r squared. Related rates, we know that we got to involve derivatives. So let's just go ahead and find each of these equations derivative. That way we have everything in front of us. Then we can gather some more information and decide what we can do to plug in and find the missing value. So let's find the derivative for v equals 4 thirds pi r cubed. Oh, I do want to point something out here. Remember, pi is not a variable, okay? So pi is just it's a constant like 4 and 3, but we're going to hold on to it like as if it is a variable, in the sense that if we hold on to pi, we can ensure we have exact value and not just an approximation. So rather than writing out 3.14159, we're going to just leave it as pi. So the reason why I want to keep bringing up the fact that it's not a variable is I don't want us to have to go through product rule, okay? We should just rely on power rule for r cubed, and 4 thirds pi is just a number that's going to attach itself to our derivative. Okay, so look at how we did a equals x squared. What do you think the derivative would be for v on the left side? What does v become?
1 dv d.
Good. 1 dv dt, right? Now again, if you want to leave out the 1, that's fine. Just want to emphasize that v is a variable to the first power, so that's why it goes to 1. Okay. We find the derivative. Remember, 4 thirds pi is just a number that happens to be attached to r cubed. So that's not going to go anywhere. It's just r cubed we got to worry about. Okay, so what's the derivative for r cubed? 3r squared, and we also need to include what?
Pi.
Yeah, dr over dt. Good, dr over dt. So every variable is going to have its own d over dt. Good. All right, we can do a little bit of cleanup, but any questions up to this point? And if you want to skip this step to the cleanup, that's fine as well. I just want to show every step. Some of these steps you can do in one step. The 3's cancel out for me here. Okay, we'll put that on hold. Come back to it later. Let's do the same thing for S. Let's find the derivative for surface area. We're going to need that as well. Okay, so S becomes
1 ds dt.
Okay, 1 ds dt. Again, I'm not consistent with the ones here. I can leave it out or put it in. It's up to you guys. All right, what about 4 pi r squared?
2r dr dt.
dr dt, good. You can, if you want to put that 2 with the 4 and make it 8 pi earlier, you can. If you want to put the 2 in front or after, it doesn't matter. Okay, so however way you want to do it, either way, We just have to make sure that really the derivative is just for that r squared, and don't forget the dr dt. Okay. Let me highlight these equations because these are the equations that we're going to potentially need depending on what the problem has for us. So let me talk about what these variables mean. dv dt is how fast the volume of the sphere is changing. dr dt is how fast the radius of the sphere is changing. ds dt is how fast the surface area of the radius of the sphere is changing. And r just represents the radius of the sphere. Okay. All right, let's go back to the problem and see what information we can gather. A balloon is being inflated at a rate of 10 cubic centimeters per second. What can we assign that number to? What variable? Any context clues there?
Volume.
Okay, I think it's definitely volume related. Okay, why is it dv dt and not just v? Yeah,
Because
you see per second.
changes.
Good. You see rate, you see inflated, you see per second. All those are things to indicate that it's not just a static value, right? It's describing some sort of a change. But yes, it doesn't say the word volume, but you see cubic centimeters, so that's an indication that we're dealing with a three-dimensional unit. Good. I just want us to be comfortable reading the problem and knowing exactly what it's talking about without having to feel like you're guessing what that value is. Okay. And do we keep that a positive or a negative rate? Because we always have to make that decision.
Positive.
Positive, yes, because
It's being inflated.
it's getting larger over time, right? If it's being deflated, then we want to make that a negative. Good. So I want to keep reminding us that we're going to have to make that decision, positive or negative, for every rate that we come across. Okay, find the rate of change of the surface area of the balloon. Okay, what are we looking for?
ds over dt.
Good. Surface area is S. You see rate of surface area, so it must be a ds dt. At the moment when the surface area is 64 pi. 64 pi is assigned to what?
It's a static value.
Say again?
It's a static value.
Yep. So it's just going to go to
This area.
S. Yep, just S. All right. We have everything that we need to solve for ds dt. Now it's just a matter of piecing this puzzle together. Okay, let's look at our problem here. We know let's start at the end, right? We know we're looking for ds dt, so we have an equation here. What information do we need to find ds dt?
Radius.
R
Radius.
and dr dt.
dr dt, right? And it would be a lot easier if they just gave those values to us for us to plug in, but it's not directly, right? We don't have those values given to us, but maybe we have something that's related to help us get to those. So do we see a path maybe? How can this information help us out, 64 pi?
We can input that into the surface area formula and find
That
out
can help you find what?
R.
Find the radius, right? And that's what we need, right? So it's not as easy as just finding that value and plugging in, but, right, we look at what we have, we look at the information that's given to us, and then we kind of map it out, right? So if I plug this into here, I can solve for R, and that's one thing that, so we see a path. We see a path towards our radius. Okay, good. Okay, what can dVdt do for us?
We can use that to find dRdt.
Good, we can find dRdt, right? So if I plug 10 in for dVdt, we need R, but hopefully we could have found R from this information. And then once we have these two, we can solve for dRdt, and then we have the pieces that we need to find our final variable. Good, so I want us to kind of see the big picture before we jump in. Okay, any questions about how we're going to move forward? All right, so now let's see if we can put it all together. I'll take that 64 pi and put it in for S. I'll put this over here. I'll insert that 64 pi in for S, and that can lead me towards solving for R. Okay. Divide both sides by 4 pi. Reduce that. Yes, 16. Take the square roots. Technically, we have plus or minus that shows up, but for our problem, we're only going to keep what?
Plus.
Yeah, just the positive 4. Good. All right, for our problem, right, it doesn't make sense to have a negative radius, so. Right. Now let's look at that dVdt, right? We're going to use this equation now. I'll put this below. I'll plug 10 in for dVdt, I'll plug 4 in for R, and then that can help me get to solve for that, work towards that dRdt. Okay, do a little bit of cleanup. 4 times 16, I get 16 pi there. I'm sorry, 16 times 4, 64 pi, right? And what can I do now to solve for dRdt? Divide both sides by 64 pi. Good. You can leave it like this, or you can reduce it, but either way, we're going to hold on to that pi. I can take 2 from both 10 and 64 to make it 5 over 32 pi. Now, this looks straightforward enough, right? But over the years, a lot of students want to rewrite this in something that is incorrect. Anybody know? Want to take a guess as to what I see every year?
What do you mean by that?
Yeah, so some students want to put this, write this slightly differently. That is going to be incorrect.
Oh, they're gonna like put it to like 100 because like 32 times 3.14 or whatever.
That's not the issue. I mean,
Would they write 5 pi over 32?
yeah, this happens. And I understand. I understand why students would do this because it just feels more natural to put the pi in the numerator, right? We're not used to seeing pi in the denominator. Or you may see this 5 pi over 32. But these aren't the same, right? Dividing by pi and multiplying by pi is going to be different. So I just want to point that out. Right, so if we divide something, if it's in the denominator, it needs to stay in the denominator. We can't move it up. Or if you move it up, you can make it pi to -1, but that's going to make things more complicated. So yeah, also, I think another instance is just sometimes people think that these are the same things, right? If I have the pi here, why not just put it over here? But denominator and numerator are going to be two different calculations. So we need to leave that. If algebraically it ends up in the denominator, we need to keep it in the denominator. All right, I think we should be able to work towards our answer, right? Because there's our DSDT. We have R that we can plug in. We have DRDT that we can plug in, and then we can solve for DSDT. So I'm running out of room here, so I'm going to put it below here. So 8 pi times 4 DRDT 5 over 32 pi. And what does this clean up to be? Yeah, 32 goes away, pi and pi goes away. I'm just left with 5. And what's our unit of measure for DSDT?
Centimeters over seconds.
Close. Surface area, though. What's the unit of measure for surface area?
Centimeter square second.
Yeah, centimeter squared. So surface area, we focus on the word area. Area is a two-dimensional unit, so centimeter squared. And then we can find the time, which is seconds. So there we go. All right, good. Any questions? Sorry, I bled into number 4 here. But number 4 is just going to be a Pythagorean theorem problem, which I want to do eventually, but we've seen Pythagorean theorem already. So we'll come back to it. And I want to focus on number 5, because number 5 is the one that requires a little bit more time. Maybe may take a couple of days for it to kind of sink in terms of just because there's so many steps. But any questions with 3? Are you guys okay here? So the recap with these problems, once I have my equation, I find the derivative. Once I find my derivative, I gather my information. And then I look to see, all right, what do I need? What do I have? How can I get from what I need? Or how can I get from what I have to what I need? And sometimes it's more than just plugging into an equation. I may need to have some intermediate steps to get to my destination. All right, number 5. Okay, let's read the problem and then talk about this concept we're going to learn about here. So we have a tank that is vertex down, so pointing downwards, 10 feet across and 12 feet deep. These are dimensions for my tank. They're not changing, right? They're going to stay 10 and 12 all the way throughout the problem. So I'm going to go ahead and label. So 10 feet across, 12 feet deep, Water is flowing into the tank at a rate of 10 cubic feet per minute. Find the rate of change of the depth of water when the water is 8 feet deep. Okay, well, let's worry about that a little bit later. But we can kind of visualize what's going on, right? Water is coming in. There's going to be some water level, and that water level is going to be rising over time. So we're dealing with the volume of this cone. So here's our formula. V equals pi over 3 r squared h. We do want to find a derivative eventually, but what is the complexity of the derivative using what we see in front of us as compared to most of the problems that we saw before? What makes this more complex than previous?
Now we have 3 variables.
Okay, and what are the 3 variables?
V, R, and H.
Yeah, V, R, and H. Now, before, I guess, if we count the left side, we always have that 1. But it's really this R squared and H, right? If we want to find a derivative, we'll have to go through what? Product rule, which in itself is not, is not something that we haven't seen before, right? We saw that with area of a triangle. But see what happened when you found the derivative. When you found the derivative, we had all these variables pop up, right? Your x and y are still going to show up. Dx dt and dy dt shows up. So you have 4 variables that's going to pop up. The reason why we don't do product rule is because we're going to see in a minute that there's just not enough information. There's going to be 4 variables that pop up, but then there's not enough information to plug in for all those missing variables. So we're going to need to find another way. And the other way is going to be finding a way to merge these 2 variables together to get this down to 1 variable. But we can't just merge them like what we see here, because these are 2 different variables. So what if we can figure out what that relationship is between these 2 variables? Then I can substitute one in for the other. Right? And this is how, and that relationship is going to be found by using similar triangles. So you guys can write this down here. So similar triangles is how we are going to, this will help us find okay, will help us find the relationship between radius and height. So let's see how we can build that relationship. We're going to draw a line down this middle here, and we're just going to focus on the cross-section, a 2-dimensional shape. So we're going to focus on the fact that we have a triangle within a triangle, and these 2 triangles that we see are going to be in proportion to each other. So I'm going to just redraw that and just focus on what I want to look at. So we have a right triangle created from the dimension of my tank, but then there's also a triangle that's created by the water level, the shape that's created of the water inside the tank. So let's talk about the dimension of this tank here, right? The height is still going to be 12, but now this is going to be what? That's the radius, right? So radius is going to be 5. So something I want to point out is that sometimes the problem gives you information about the radius. Sometimes it gives you the diameter. You have to read the problem and actually just focus on that, right? Don't assume that whatever number you see at the beginning is a diameter. Sometimes it's the radius. 10 feet across would be diameter. If it says the radius is 10 feet, then you'll make that 10. But yeah, just pay attention to the values that they give you. But what about the radius and the height of the water, of the triangle created by the water level? Are those going to stay constant? Yeah. Yes, right. So water's flowing in, so we know that these values are not going to stay constant. But that relationship, you're right, that relationship is going to be built because of the fact that these two triangles are going to be in proportion to each other. And that's how we're going to build that relationship, and that's how we're going to get one variable in terms of the other. Okay. And also, this equation, this R and this H is talking about the water level. Okay, it's not talking about the dimensions of the tank, because we don't need that, right? We already have the dimensions of the tank. The R and H that we're concerned about is the height and the water and the radius of the water level. So we can say this. Based off this diagram, we can say radius of this triangle or water level is to the radius of the tank as the height of the water level is to the height of the tank. So this is now the relationship between R and H. Okay. If I do cross product, I can get that denominator to go away here. So now the next decision is, which variable do we want? Do we want this in terms of H, or do we want this in terms of R? And we're going to have to go to our problem and gather some more information. But eventually, we're going to have to use this to help us get this down to one variable. There's too many variables here. Okay, so back to our problem here. We have the dimensions of the tank. Next sentence. If water is flowing into the tank at a rate of 10 cubic feet per minute. Okay, so what do we assign that to? Maybe the variable hasn't shown up yet, but we should be able to assign it though.
dV dt.
Good. Cubic feet, we know that's volume. Per minute, that's a rate, so it must be dV dt. Positive or negative?
Positive.
Yeah, flowing into the tank, right? Water is accumulating inside the tank. Find the rate of change of the depth of water. Okay, so that's what we're looking for here. So what is that talking about? What's depth of water talking? What variable is that referring to? H. So
H.
yep. And now rate of change of that must be GH dt.
GH dt.
Good. DH over dt. Good. Okay. When the water is 8 feet deep. So 8 is assigned to just what? Just H. Yep, just height. Yep. So look at what information is provided for us. how do you think you want the volume equation to look? Would it be more helpful to get everything in terms of H or everything in terms of R?
In terms of R.
So we want this to help us with our derivative and with our work. So if we get this in terms of H, we're going to be able to naturally produce a dHdt out of it, and that will just naturally show up. If we do it in terms of R, then our dr dt will show up, which we can still get the dHdt, but it's just a longer path. So I would say this, whatever information is given to you or whatever information is provided, that's going to help guide how you want your volume equation to look on the right side. So this is what we want to do. Okay, so we want this to be in terms of H. So that means I want to find a way to replace my R. I want to remove my R. Now you could get everything in terms of R. It's just there's just more steps involved. It's just not as efficient. The fastest way to our answer is going to be through H because we have H information already. Okay, so I do want to back up for a moment before we look into that substitution. And I want to talk about this H equals 8. This causes a lot of mistakes, so I want to make sure I bring that up. So what I want to say about this H is do not use until the very end. Okay. Basically, you're not going to use not until after the derivative has shown up. Let me talk about why that's the case. H equals 8 represents the height of the water level at any given at a specific moment in time. But is the water level going to always remain at 8? It's going to be changing, right? So a lot of students want to do this. A lot of us want to put that 8 wherever we see the H. But if we put the 8 in for the H, that means we're saying that the problem is not, that means that there's a constant here. That means this height, as water is pouring in, this height is not going to change. It's going to remain at 8 for the entire problem. And if we do that, then we're changing the problem, right? We're not solving what it's asking for us to find. We are going to use this, but we need to hold on to these variables because these variables indicate that the height is still changing, right? It is still a work in progress. But after, when the derivative shows up and we've established all the relationships and we're ready to find the value, then we can plug that 8 in. But the tendency is we want to plug that in too soon because it's right there, right? It's like, why not plug in 8 for H when these are all the variables that we see? But we're going to ignore these. We're going to ignore this until the very, very end. Okay. All right, so back to what we are trying to do here. We're trying to get this in terms of H. So I want to solve for R. If I solve for R, I can replace R, and then I can get this right side to be just H's and no R's. So I'm going to solve for R here. R is equal to 5H over 12. I'm going to take this and plug it into here. Make that substitution. No derivative yet. I'm just trying to clean up my right side here. Pi over 3, r squared. My r is 5h over 12 now. All right, any questions so far? Good. Now, technically, you could find the derivative here, but my suggestion is this is still too messy. Okay, you could go through product and chain, but we should be able to get this to the point where the only thing we need is power rule. We should have a nice, clean derivative rule. We shouldn't mess with this whole thing. Also, sometimes students want to find the derivative here and they do it wrong because they find the derivative of both of these and they forget about product rule, and that messes things up too. So we do want to clean up either way. So the nice thing is that this exponent can distribute through the parentheses. There's no plus, there's no minus, there's no subtraction, addition. So we can distribute without breaking any rules. There's no need to go through any messy expansion rules. We just distribute that exponent through. So 5 squared, h squared, 12 squared. Okay, still kind of messy, but we're getting there. Why don't we push all the coefficients together, and let's put the variables together. So what can I do with h squared and h? This combines to be what? H cubed,
H
right?
cubed.
Add exponents. 2 plus 1 is 3. And I can put the 25, the pi together. I can put the 4 times 130, sorry, 144 times 3 together, which is 432. So I am getting closer to being ready for power rule. Now, if you look at this, this is a lot cleaner than here. All these you can find the derivative, but this is going to be the easiest to do for derivative. That's just a number in front of h cubed. We just do a simple power rule for h. Okay, any questions up to this point? All right, let's find the derivative. V becomes dv over dt.
dv dt.
Good. This messy fraction stays, right? It's not going to go anywhere. And then h cubed becomes what? And don't forget 3h squared times dh over dt. All right, our path to our answer is going to be a lot cleaner now, a lot more straightforward. Any questions up to this point? If you want to clean this up further, you can. Or we can start plugging in, but maybe I'll clean up a little bit more. I'll put that 3 with the 25. I'll make it 75 pi, but from this point, you can really just do whatever you like in terms of the order of cleanup or substitution. Okay. We found the derivative. Now we can use what? And we can use, yeah, now we can use that 8, right? I said don't touch this until the end. Now we're at the end. Now we can use that 8. So 8 doesn't go here. It doesn't go here. It doesn't go here. It doesn't go here. It doesn't go here. Once that derivative shows up, then you're okay. Then you're okay with using that 8 in. All right, and then the 10 can replace dv dt as well. So use your calculator, but hold on to pi. So we want to hold on to pi. We're going to represent pi in the final answer. That is also the case on the AP exam as well. They want you to hold on to pi and as the answer choice. So let's see what we can do here. If I plug in the calculator, 75 times 64 over 432, I think that cleans up to be a nice fraction. Or does it? Let's see. 4,800. Okay, maybe you have reduced it further, which is fine. Either way, I have to move this over to the left side, right? So dividing by a fraction is the same thing as what? Yeah, dividing by a fraction is the same thing as multiplying by the reciprocal. And that just makes it a little bit easier rather than having to divide it by 4,800 over 432 pi, or sorry, 4,800 pi over 432. We can have it as, now, maybe you've reduced it earlier already, which is fine. I've just left it in that form here. So I get 0.9 or 9 over 10. Okay, where does the pi go? Denominator, yeah. I know this is strange, right? We're not used to seeing pi in the denominator, but that's where it ends up, so that's where it needs to stay. And what's our unit of measure? Height is in terms of what unit?
Some feet.
Feet, yeah. It's a one-dimensional unit, right? Only area and volume do we do anything additional, right? One-dimensional unit, so just feet, and then time is what's time? Minute, yeah. Feet per minute. Okay, as you can see, a lot of things to do with this problem, right? So we need to spend a couple of days kind of practicing through this and knowing how to move through. Okay. All right, any questions for now? Okay, so no homework tonight. Tomorrow we're just going to focus on these topics. I have another worksheet that was under today's link. Hopefully you guys printed it out. We'll be able to use that tomorrow, which is, it says quiz review, but we're not gonna have a quiz over this. We're gonna have a test sometime later next week, which is called a test, but we're not gonna have a quiz, and we're just gonna have one assessment for related rates. So, all right, thanks everyone. Hope you guys have a great day. See you guys
Have a nice day,
tomorrow.
Mr. Yang.
Thank you,
Thanks,
Mr.
guys.
Yang. Have a nice day. See you tomorrow.
See you tomorrow.